My name is Erji. I'm from South Korea. I'm a physics and mathematics major here in ASU, and I design software that helps data collection.
Hi, my name is Seth Dimery. I'm from Water Valley, Texas. I'm a junior here at ASU studying physics, and I put together the apparatus for our project.
I'm Marcus Morales. I'm a junior at Angelo State, and I study physics and chemistry.
Hello, I'm Eduardo Giro Serrata, and I'm an international student from Chihuahua, Mexico. I'm a junior here at Angelo State University, and I help with the research on iron dope materials.
Our objective this semester has been to test the viability of 3D printing electromagnetic energy shielding using ferromagnetic plastic. Being able to replace shielding of sensitive electronics during long-term missions is imperative, and so having a more mass-efficient method of printing new shielding instead of carrying replacements would be ideal. Angelo State had no equipment for testing how effective our shielding would be, so we engineered our own network analyzer consisting of a radio receiver and transmitter with a coupling to insert sample prints into the center. We used a Lulzbot TAS6 printer to create sample shielding using protopasta magnetic iron PLA with varying infill properties. Using a macro program and software controlling the transmitter and receiver, we tested permeability across the 1.3 to 1.7 GHz spectrum. 3 variables were tested for efficiency: sample thickness, infill percentage, and infill line thickness. Similar to the spike-like walls or ridging patterns of acoustic panels, geometry can greatly affect absorption and reflection. Ultimately, magnetic PLA was determined not to be a viable material. However, the insight into real-world research and development processes was invaluable.
We started the next semester finding the optimal position for our transmitter and receiver. We also had the goal to test iron-doped paint as well as non-conductive sheets. However, we were unable to get to these due to the coronavirus.
Upon encountering several problems when testing, the left shift of the frequency in our graph became the most problematic one. Eventually, and with more testing, we realized that this issue was originated from the material we used. Therefore, this material delayed the wave, which made our resonance frequency shorter. Hence, our graph shifting to the left.
The resonance frequency becomes elongated whenever a material is in between. The signal has a time delay, so it no longer travels at the speed of light.
With this assumption, we could measure the attenuation using the mean of the complete frequency range as well as the frequency shift. In the end, we found out that the resonance frequency of our material is 1.555 plus or minus 0.007 GHz. We can now conclude that near this frequency range, the shift was smaller, but as the frequency got farther away from this range, our shift would become larger.
One of our tests for radio wave shielding included iron-doped paint applied to a thin 3D printed PLA plate. This idea was brought up because of the ease of application and accessibility. However, we weren't sure if it had the capability of blocking many waves, or if it would even be able to withstand temperatures and conditions. The plan was to use liquid nitrogen to freeze the paint to see if it would still last in harsh conditions. Unfortunately, due to the coronavirus, we were unable to test the iron-doped paint. For further testing, we bought a 210 by 297 mm RF EMI absorbing sheet that was non-conductive. We bought 2 others with various thicknesses. However, we were unable to get to these due to the coronavirus. Our future objective is to continue testing and to find the ideal material that would block radiation.